Okay, so this is how we're going to do the actual teaching. Normally I would be writing on a board, but since that doesn't work so well online, I actually have a board in my office, but I think if I try to write on this board and have the camera pointing at the board, I don't know if the camera would be good enough. So instead of that, I have prepared handwritten lecture notes going through all the topics of the course, which I'm taking pictures of and uploading before each class. So during the class, I'm going to open these from my computer because then I can edit things if necessary. Sometimes I might want to type something, just add something here. Sometimes I might want to maybe draw a little picture. So I'm opening this in Paint so that I can edit it if necessary, maybe underline something, draw something, write something extra. I want to make the classes a little bit interactive because when I'm writing on the board, you can be taking notes from the board, that's fine. But when it's just like this, I don't want you to just sit and look at a page that stays the same when I'm talking, and I understand this can get boring. So I'll try to make it interesting and sometimes add things or write extra things. That's why I'm opening this just on my computer, but after the class, I will upload these pages, including the edits, into Teams. So if you miss a class, you can still be able to sorry, not into Teams, into Moodle, I mean. File uploading is through Moodle. So if you miss a class, you can catch up by checking the uploaded files. I'm also recording this video, which stays available in Teams for 3 weeks. So you can find the videos in the meeting chat and you can download from there up to 3 weeks after the class. Somebody mentioned getting an error from trying to fill in the attendance. So if you try to fill the attendance and it gives you an error message or you can't manage to do it, then just leave a message below the form and say that I'm here, but I couldn't manage to fill the form, and then I will add your name to the attendance. Just before we start, I see another hand raised from Savash Mutarolu. Do you have a question?
Oh, sorry, I don't.
Yes?
I don't have questions. Right now, I don't have.
Sorry, one moment. Sorry, just someone came to my office for a minute, so I had to answer him. Okay, so coming back to these notes. Yeah, so this is how I'm doing it. I'm sharing these pages. I will go through in the class, maybe adding some things, editing some things, then I will upload after the class. So we're going to begin the course with some introductory topics, like pre-calculus, we can call it, just to make sure everyone has the same basic knowledge. So in today's class, I'm going to go quite quickly through a lot of topics about functions, equations, graphs, etc. I'm going quickly because I'm hoping that most of you are already familiar with this. But if you are not familiar with these things, I will upload the notes so you can read through them later at whatever speed you need. I'm going to take this 2 hours class today, going through 10 pages. Hopefully, if I can manage to finish these pre-calculus things, going through these 10 pages of notes, and then next week we can start on calculus proper. We will start doing limits. So this stuff is important background for calculus. You need to know what functions are, what graphs are, and so on. You need to know these things to understand calculus. Most of this course is about functions. All the things we're going to do, differentiation, integration, and so on, they're differentiation of functions, integration of functions. So let's start by talking about functions, their equations and graphs. What is a function? This is something I want to spend a bit of time on because some people don't know the difference between a function and an equation, and this can be taught sometimes in different ways. But what a function really is, mathematically, is a rule for transforming a number into another number. So a function is just a rule. It inputs a number, you apply this rule, you apply some process of calculation, and you output a new number. So you have a function f mapping between two sets. Sets are just collections of numbers. If you have a set x and a set y, then a function from x to y is a rule which applies to any number in this set x. You can pick any number in x, any little x, which is an element of this set, and the rule will apply to this number, will send it to another number which is in the set y. And this transformed number we can write as f of x. So f brackets x, it means f of x, and that's what we call the function f applied to the number x. For example, we have the function that sends x to 5x. So we can write f of x equals 5x, and that's the function which sends any number to 5 times itself. So you input a number, you multiply it by 5, and you output the new number. G of x equals x squared is another function. It sends any number to its own square. So you input a number x, you square it, square. X cubed minus 3x, this is another function. That of course should be h and not f. Written the wrong thing there. So h of x equals x cubed minus 3x. And that means if you input any number h, you calculate, sorry, if you input any number x, you calculate the cube of x, you subtract 3 times x, and you get a new number, which is the output number. So the important thing about functions is that when you input a number, you always have a single output number. F of x is a well-defined number. You cannot have two possible numbers f of x. It's just one number. F of x is defined in this particular way. Notice that, for example, taking this function g, it's possible to send two different numbers to the same output number. If you have the inputs 2 or minus 2, then the output 2 squared and minus 2 squared, they are both 4, they are both the same thing. And also there are some numbers which cannot be outputs. For example, x squared cannot be negative. So minus 1 is not in the possible output numbers. Sorry, I'm just, okay. Got a notification from Teams again. I was wondering if it's someone here, but okay. Right, so now we know what a function is. The domain of a function is the set of possible input numbers. So the domain can be given either explicitly or implicitly according to how the function is given to you in a particular problem. So function including the two sets, if you're given a function as f from x to y, then its explicit domain is simply the set x. You're given the set x that it maps, that this function applies to, and that's the domain. But not given the sets, at least in this course, you would normally be given a function just by how it works, like the function 5x or x squared or x cubed minus 3x, just by the nature of the rule. It's the function, the rule that sends any number to 5 times itself. That's the number 5x. This is defined without bothering to specify sets. And the same with these others. Each definition here is saying what the function does, how the rule works, but it didn't bother to say which sets it is going between. And if you're given a function in this way, then you need to use its implicit domain, which is just the set of all possible input numbers, all real numbers x, such that f of x can be defined. So these three functions we've looked at above, they can be defined for all possible numbers x. You can take 5 times anything, you can square anything, you can cube anything and subtract 3 times anything. All of these things, there are no restrictions. So the domain is the set of all real numbers, which we write as R, Blackboard bold R. See the double line there, it's a special font of R, which means the set of all real numbers. But not all functions are defined everywhere. So you can have a function f of x equals 1 over x, and this is not defined at x equals 0, because you cannot divide by 0. 1 over 3 is defined, 1 over minus 3 is defined, 1 over 7 is defined, 1 over pi is defined, 1 over 0 is not defined. So for all real numbers except 0, this function is okay. So that means the domain is everything except 0. It's real numbers without just 0. F of x equals square root x. This is another function which is not defined everywhere, because you can take the square root of a positive number, you can take the square root of 0, which is 0, but you cannot take the square root of a negative number. So the domain is the set of all non-negative real numbers. It's real numbers which are positive or 0. That's the domain of the square root function. That's the set of all numbers whose square roots can be defined within the real numbers. Okay, so that's the domain. It's the set of possible input numbers. Then what about the set of possible output numbers? This is something that we call the range. So now I'm going to stop sharing for a second and move to the next page. Page 2. Okay, so the range of a function is the set of all possible output numbers, and that means the set of all possible numbers f of x. So you have a function mapping from the set x into the set y, then the range is a subset of y, it's inside y. Sometimes that range is all of y, and sometimes it's not, sometimes it's a smaller thing. So for example, the function 5x has range r because every number is 5 times something. If I give you any real number, that's 5 times some other number. And remember that we're looking at real numbers here, not whole numbers. So 1 is 5 times 0.2, and 7 is 5 times 1.4, and so on. G of x equals x squared. That's the square function. This does not have range all of r, because a square number cannot be negative. After you square something, the square is either positive or it's 0. So the range is only the positive or 0 real numbers. It's not all real numbers. It's not negative numbers. This third example function, x cubed minus 3x, I'm using these 3 examples a lot because they show various types of behaviors. This example function has a range which is more difficult to find. Actually, the range is all real numbers, but this is not obvious. So you can't just look at this function and say any real number must be expressible as something cubed minus 3 times itself. But after we've learned some techniques of calculus, after we've learned about limits and differentiation and curve sketching and all these topics, then it will be easy to find out that the range of this function is R. So this is one of the places where calculus can help. If you're given a function, you can find these properties, find out what is the domain and the range using techniques of calculus. Okay, now some other things about a function. We say a function is surjective. Okay, let's scroll to the top again, sorry. A function is surjective or onto if its range is all of y. And it is injective. Okay, let me start to draw a little picture here. So one way of understanding a function is that you have a set x you have a set y. So this is x, and this is y. And I'm going to show each of these sets just by a sort of bubble which has various numbers in it. So these points represent numbers, and the bubble represents a set. So, yeah. So a function is starting from any point on the left, any point in x, and sending those numbers to somewhere in y. So I'm going to put little arrows on here. So you could say that a function is a collection of arrows between these two sets. Every number in x goes somewhere, and somewhere in this second set y. So this could be a function f, which sends x to y. Now, surjective is about the range. But what is the range when you understand the function using this picture? Well, the range is the set of all the points which are actually hit by some arrows. Okay, so this point is hit, this point is hit, this point is hit, but that point is not in the range. And because of that, this means that is not surjective. So you're just trying to squeeze this in. Okay, because of that point, this function is not surjective because there is a point in y which is not hit by any arrows. Okay, surjective is relatively easy to understand. Injective is a bit more tricky. So we say a function is injective or one-to-one if you never have two numbers in x going to the same number in y. So that's actually what is happening at this point. You have two different arrows coming into the same point. And because of that, that means that this function is not injective. Okay, so injective means that if you have two different numbers in x, they must go to different numbers in y. You have x1 and x2, they're not equal to each other, then f of x1, f of x2 must be not equal to each other. So that's what injective means. In terms of this picture of a function, numbers mapping to numbers like this, anything which has more than one arrow is not injective. Anything which has less than one arrow is not surjective. But remember, these properties of surjective and injective, they're not just about numbers or points, they're about the function itself. So what this means here, we're not saying this number is not injective, this number is not surjective. We're saying the function is not injective and it is not surjective. So you can also have a function which is let me zoom up a bit to make this more clear. Okay, so here I'm going to draw a function which is surjective, but it's not injective. So here we have again set x, set y. I handwriting gets a bit crazy when I'm writing using Paint. Okay, so you've got two sets, you've got a function going between them, and this function is surjective because everything in y is hit, but it's not injective because you have these two different x going to the same y. So this one is surjective, not injective. Then I can draw another function which is injective but not surjective. Okay, so here's two functions. Now this one is injective because all of the points in y, they've only got one arrow coming into them, but it's not surjective because that point there is not hit by anything. I'm just pointing again to the one here. This stops the function from being injective, and this stops the function from being surjective. So right here, this is injective, but not surjective. And finally, we say that a function is bijective if it is both injective and surjective. So I'll draw quickly an example of that. So here is again some function, some arrows going from left to right, and overall you get a function which is injective, surjective, and therefore bijective. Okay, so I've shown you in this little piece on the right, here is a function which is not injective, not surjective. Something is mapped twice, something is not mapped at all. This one is surjective, not injective, because everything is hit by some arrows, but something is hit twice. This is injective, not surjective, because nothing is hit twice, but something is not hit at all. And this one is bijective, because every point is hit by exactly one arrow. So for example, the function, let's look at this bottom example first. The 5x function sends every number to 5 times itself. That's bijective. Everything is 5 times something, as I mentioned before. Every number is in the range. Everything is 5 times something. That means it's surjective. If you take two different numbers, multiply them by 5, the result must be different. So you never have two different numbers mapping to the same place. Therefore, it is injective. So that's a bijective function. Note that these properties of surjective, injective, bijective, they depend on the choices of sets x and y. So if you have a function f from x to y, then whether that's injective or not, whether it's surjective or not, depends on which sets you choose here. For example, let's consider the x squared function in 4 different ways. G of x equals x squared in all of these 4 cases, but we're using different sets. So let's first do the simple thing of just taking g from real numbers to real numbers. So g of x applies to any real number x, and the result is another real number. Now this is not injective and it's not surjective. because g of 3 and g of minus 3 are the same thing. That means it's not injective because you have two different numbers mapping to the same place under the function. But it's also not surjective because you have g of nothing is minus 1. Minus 1 is not in the range. There is no real number x such that x squared equals minus 1. Minus 1 is not in the range, so it's not surjective. 9 is in the range twice. It's hit by two arrows, so it's not injective. Now let's try restricting the set y. So because every square number is either positive or 0, we can take our set y to be just the positive and 0 reals. Ignore the negative numbers because they're not in the range anyway. And now the range is exactly this set y. So if we choose a different set y, then suddenly it is surjective. But it's still not injective because we still have this problem. G of 3 and g of minus 3 equals 9. So in this set y, everything is hit, so it's surjective, but 9 is hit twice, so it's not injective. Then for this function, we've now restricted the domain. So I'm giving you an explicit domain, which is the smaller set of just positive or 0 numbers. So again, that works. You can take any positive or 0 number x, you can square it, you get another real number. Now this function is injective because you can't square two positive numbers and get the same thing. If the square of two numbers is the same, then one of them is positive, the other one is negative. You have two different positive numbers, their squares must be different. So by restricting the domain, we can force it to be injective, but it's still not surjective because this set y includes numbers like minus 1, which are not covered by the function. They're not hit by any arrows. And finally, when you go from r plus 0 to r plus 0, from positive or 0 reals into the positive or 0 reals, then that is completely bijective. It's injective and it's surjective, therefore it's bijective because you don't have this problem anymore. Nothing is hit more than once because we're mapping from the domain on positive numbers, and also nothing is not hit because we're mapping into just a set of positive numbers. So in this set, from this domain, every number is hit exactly once. Okay, these topics, these concepts are a little bit difficult to understand. That's why I'm trying to give lots of examples here and to discuss the examples at some length, because they're good concepts to understand, but it takes a little bit of effort and a little bit of practice. So, I mean, go and look at some other functions. You can find examples also in the textbook in chapter 1, discussion of injectivity, surjectivity, bijectivity, and what these things mean and how they apply in specific cases. For now, let's leave functions for a while. As I said, most of this course is about functions. So these are very important things to understand their properties, to look at important types of functions. But for now, let's go and talk not about functions, but about equations, which connect strongly with functions. So there is a connection, it's just not exactly the same thing. So I will stop sharing this page and I'll open the next page. Okay, here we have page 3. So let's just start with what is an equation. An equation is when you write that two different expressions are equal to each other. these expressions usually involve some variables, maybe just one variable x, maybe two variables x and y, maybe even more. An equation of one variable x, this is something that can be solved to find some specific values of x. For example, x squared equals x is an equation. Its solutions are x equals 0, x equals 1. Because 0 squared equals 0, 1 squared equals 1, and that equation is not true for any other number x. X cubed minus 3x equals 0. That's another equation. You've got two different expressions on the left and right of the equal sign. So it's an equation. Again, it can be solved. There's three possible values of x. X equals 0, x equals root 3, x equals minus root 3. Those three numbers make this equation true, and no other numbers can work. So these are the only solutions. If you have an equation in two variables, x and y, this does not give you specific values, so you can't solve it to say x equals this, y equals that, but it describes a kind of relationship between x and y. For example, you can have an equation like y equals 5x, which gives you the relationship that one of them is always 5 times the other. Or you can have y equals x squared, which gives you the relationship that one of them is the square of the other. And here are some more examples. See, it can get a bit more complicated. Sometimes you can get x and y appearing on both sides of the equation. All you need is to have two different expressions. It's not necessarily y equals something. And you can have an equation like this, where the relationship is that when you square them and add them together, you always get 1. Okay, now if you look at the first three of these examples, they might look familiar because they are the things we have been studying as functions. On the previous pages, we looked at f of x equals 5x, g of x equals x squared, h of x equals x cubed minus 3x. We studied them as functions, and now they've cropped up again as equations. In fact, every function, because if you have a function f, that's a rule applied to some numbers, and you can write the equation y equals f of x. So from the rule, you get a relationship. The relationship being that y is you get from applying the rule to x. Okay, y equals f of x is the equation from a function. But not every equation gives a function. So if I give you a function, you can give me back an equation. If I give you an equation, sometimes there is no function. And let's look at these two equations. One of them gives a function, the other one doesn't. How do we see that? Well, consider the first one here. We can rearrange this equation to put y in terms of x. Start from this equation, x squared plus 2y equals 1 plus x. Subtract x squared on both sides of the equation, and you get 2y equals 1 plus x minus x squared. Then divide by 2, again on both sides of the equation, and you get y equals 1 plus x minus x squared over 2. And this expression, or specifically the right-hand side of this, is a function. That's a function of x, and this is an equation which is equivalent to the equation we started with. They mean exactly the same thing. So we have rewritten this equation to give y just in terms of x, which is a function. It's in the form y equals f of x. But this last example, x squared plus y squared equals 1, that does not give a function. How can you see it definitely does not give a function? Because you can get the same value of x with two different values of y. See, if x equals 0, then y equals 1 is a possibility, y equals minus 1 is a possibility. 0 and 1, you square these things, add them together, you get 1. 0 and minus 1, you square them, add them together, you get 1. So both of these are pairs of numbers which satisfy the equation. They satisfy this relationship, but you've got the same value of x with two different values of y. So if you imagine writing y equals f of x, that can't work, because then f of 0 equals what? 1 or minus 1. You could have y equals f of x, but then 1 equals f of 0 from there, minus 1 equals f of 0 from there, which is impossible for a function, because a function should take an input number and it should give you an exact rule for finding the output number. So if you're inputting the number 0 and you can output either 1 or minus 1, that's not allowed. That's not a function. So we've seen how some equations give functions and some equations don't give functions. So that's the relationship between functions and equations. That's why sometimes there is some confusion, because some people think that y equals f of x is the definition of a function. They will define a function like this, but actually the function is defined by the rule of sending x to x squared. Y equals x squared is technically an equation. Okay. I just saw a message in the meeting chat. Can you re-explain this last point? So which point is that about whether an equation can give a function or not? So yeah, okay, this is a bit tricky to understand. I guess that the most difficult part to understand is an equation which does not give a function. So let's have a look at this equation. X squared plus y squared equals 1. Why does that not give a function? Because imagine it gives a function, then you have y equals f of x. Like with this equation here, we started with an equation and we rewrote that equation in an equivalent form as y equals f of x as a function. So let's say we can do the same thing here. We start with an equation and we rewrite it y as a function of x. But a function is a rule. So a function inputs one number and it tells you exactly what new number must be output. And if y equals f of x is equivalent to x squared plus y squared equals 1, then that means any pair of numbers satisfying this equation, this relationship, must be given by this equivalent equation. So that means x equals 0, y equals 1 is a pair of numbers which have this relationship. If you plug x equals 0, y equals 1 in there, you see the equation is true. X equals 0, y equals minus 1 is another pair. So these are two pairs which have the relationship given by this equation, but x equals 0 is the same in both of them. So then what is f of 0? It could be 1, it could be minus 1, because 1 equals f of 0 should be satisfied by this equation according to this pair of points. But from this pair of numbers, minus 1 equals also be satisfied. And you can't have two values for f of the same thing. Hopefully that makes it clear, because a function, remember, is a rule, and that means sending any particular number I give you, any particular x, it sends that to something. So it should send 0 to something. Okay. Then let's continue now with graphs. So graphs are very important because this is a way of understanding functions or equations by pictures. So a graph takes place in the xy plane, which is a two-dimensional plane with x coordinate and y coordinate. Probably you're already familiar with this. Every pair of numbers x and y corresponds exactly to a point in the plane. So you have negative x to the left, positive x to the right, negative y down, positive y up. So if I choose any random point in this plane, like here, that's over to the right and a bit up. So it has a positive x coordinate and a positive y coordinate, but the y coordinate is a bit smaller than the x coordinate. So you could say, for example, it's 5 to the right and 3 up. So that's the xy plane. How do we make the of an equation? Let's start by thinking about equations. So an equation is a relationship between x and y. And what we have here in the plane is all the possible pairs of numbers x and y. So any number x, any number y, if I give you two real numbers, they correspond to a point somewhere in this plane. So how can we describe this relationship? Well, we can mark all the points in the plane which satisfy the equation. So you just put a dot at every point x, y, such that the equation is satisfied, or such that x, if you're given a function to begin with. And these things are going to form normally a path or a curve in the xy plane. So you mark all these points and they join together and they form a nice curve like this, or like this, or like this, and the shape of that is according to the nature of the equation or the nature of the function. So here's y equals 5x. That's a simple function, simple equation. The relationship is that y is always 5 times as big as x. So that means if you go a bit to the right, increasing x, then you increase y 5 times as much. So you go 5 times as much up. If you go a bit to the left, then you go down. And so what we have here is a straight line. This is one of the simplest possible types of functions or equations, is just a straight line graph. Then y equals x squared gives this kind of bowl shape. Y is always positive, so y goes up to the left or to the right. Both ways it goes up. Y equals x cubed minus 3x. This one's a bit more complicated. You can't see, you don't have the tools yet to know that this is a shape, but once we've learned some more calculus, we will be able to understand how functions are shaped in their graphs. This is the difference between plotting and sketching a graph. When you plot a graph, then that means you plot exactly all the points. All the points to satisfy the equation, you join them up and you get some curve. Now that can be done by a computer, or if you have a big sheet of graph paper, you can spend a lot of effort marking all these points and joining them together. But is less exact, but it needs less effort, and you need some more understanding to be able to do this. So sketching means you don't have to show all the points exactly, but you show the overall shape. See, this is not exactly right. I've just drawn it by hand. Maybe the shape of the bump here is a little bit more stretched or a little bit more this way or that way. It's just a rough hand-drawn graph, but it gives you the important properties of the function. It shows you that the graph goes down on the left, it goes up on the right, it has a bump up there, it has a bump down there, it crosses the x-axis these 3 times. All of these are important properties of the graph, which come from the properties of a function. And a lot of what we're going to do in this course is discussing the relationship between graphs and functions or equations. So many times we will define something, like later on we can define, for example, continuity. We can say a function is if blah, 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 some kind of formulae. Or a function is continuous if its graph looks like blah, blah, blah. So you can define things using formulae and algebra, or you can define things using pictures and graphs. And it's good to have this correspondence to understand that every property of a function, every property of an equation can be shown somehow in a picture, in a graph. And that's one of the big goals of this course, is to understand all these connections. So after about 6 or 7 weeks from now, I will be able to give you a function like this, and you can use a few calculus tricks, and you can easily find the shape of the graph. You might think now that this is difficult, like how do you get this shape just from knowing that one number is given by cubing another number and subtracting 3 times it, y equals x cubed minus 3x. But after we know differentiation and extreme values and all these curve sketching things, then you'll be able to see this function and do a few quick calculations and draw this graph. So that's something to look forward to in the future, understanding how to show functions and equations by pictures. So I think I will stop for a break there. We've reached 3:20. So I said before, I'm going to normally give you a break in the middle of each 2-hour class. So I'll stop recording now.